Today we are working with rational functions. Okay? What I'd like you to do is type in number 1 into your graphing calculator. What we're going to take a look at is we're going to take a look at any vertical or horizontal asymptotes this one might have. And we're going to talk about the rules for horizontal asymptotes. So I'm going to hit alpha y equals enter. I'm going to type in the number 4. Go down here, type in x squared plus 1. I'm going to make sure my grid lines are turned on. They are. I'm going to hit zoom, number 4. Take a look at the graph. I want you guys to understand that as you look at this graph, does it look like there's any breaks in the graph? Mm-hmm. There are no breaks in the graph. That means there are no vertical asymptotes. So right here, what I'd like you to do, for asymptotes, for vertical, there are none. Okay? There are no vertical asymptotes in the graph. Does it look like it's continuous? Mm-hmm. So if it looks like it's continuous, which it is, what would our domain be?
Negative.
Right, all real numbers. Negative. So you're right, all real numbers. You're also right. Negative infinity to positive infinity. So I'm going to put negative infinity to positive infinity. I really want you guys to practice your interval notation for the domain. Okay? This would be your answer for the domain. If it was in set builder notation, you'd write the set of all x values such that x is simply an element of the real number system. That's all real numbers right there. Now, for asymptotes, there are no vertical asymptotes, but there is a horizontal asymptote right here. This graph never crosses over. All right, so we need to talk about the rules for horizontal asymptotes. This is where you need your journal right here. Okay? So I want you guys to write horizontal asymptotes. All right, so we have rules for horizontal asymptotes. So I want you guys to imagine that you have some rational function. So in our function, this one, we had f of x equals 4 over what? Over x squared plus 1? Mm-hmm. Now, what I'd like you to do for your journal, put 4x to the 0. Because technically, right here, the degree for this is actually x to the power of 0. Because x to the 0 is just equal to the number 1. This is the scenario in which m is less than n. Now, what the heck are you talking about? Well, this is m, this is n. In our situation, m is 0, n is 2. Well, 0 is less than 2. So I'm going to put if n is less than n, which means if this exponent is less than this exponent, then f of x will equal 0, which means y equals 0, which means your horizontal asymptote is y equals 0. So this is the situation where your horizontal asymptote is at y equals 0. If m is less than n. So if you have this situation, it will always be, and you have a rational function, then f of x will equal a 0. All right, here's one more example. Okay. If I had f of x and I had 5x squared plus 1 over 2x minus a 2. All I'm worried about is this exponent in comparison to this exponent. Because right here, 2 is less than 3, my horizontal asymptote would be at 0. That's where the horizontal one. Put H, A, short for horizontal asymptote, not Latin actually. Okay? Horizontal asymptote. So that's one rule.
Why was it 0?
Because this exponent is smaller than this exponent. Okay? That's another scenario. What if it was bigger? Okay? We'll get to that one. There's 2 other scenarios. One scenario, that if m is equal to n. This is the second scenario. If m is equal to n, let me rewrite the function. If you have any rational function, f of x equals a times x to the m over b times x to the n. I'm just going to put plus dot dot dot. Like it's just in this rational function form. If these are exactly the same, they're the exact same number, then your horizontal will always be whatever A is divided by whatever B is. If you want to, this is, if m is equal to n, then f of x equals A over B. I'm going to give you an example of that one. All right, so what was our horizontal for number 1? Our horizontal was what? It was f of x equals 0. You can also put y equals 0. That was this one. What I'd like us to do now is I would like us to go to number 2. All right, let's graph that one. Here's our first one. Now we're going to graph our second one. So right here, go to y equals. Clear this out, hit alpha, y equals enter. In the numerator, it looks like we have a 2x plus 1. In the denominator, we have an x plus 1. Now if we take a look at this right here, this is our function. F of x equals 2x plus 1 over x plus 1. What's this power? This power is a 1. This power is a 1. These are the same power. This is our... So this follows the second rule. And the second rule is this. It's just going to be the A value over the B value for a horizontal asymptote. So our A value is 2. Our B value, you can't see it, 1x there. So our horizontal asymptote will be 2 over 1, or just a 2. So if we graph, it's kind of hard to see. You're like, well, I don't see a horizontal asymptote. Well, it doesn't draw it in. But we do know that 2 divided by 1 is 2. And when you hit graph, can you guys see now that this graph gets really, really close to where y is equal to a 2? Now, look what happens when I change it. If I change that to the number 5, what would my horizontal asymptote be now? It would be a 5, because 5 divided by 1 is 5. I'm going to hit zoom and number 6. Take a look at this one. Okay? If I hit y equals and I go up here and I say, you know what, Mr. Mood, what if I type in a negative 2x plus 1? Then I need to change my horizontal asymptote to a negative 2. Everybody see how the pattern works then? We good? Alright, let me go back to our original question. Delete this. This was our original line, right? Or not our original rational function. And our asymptote was at a 2, not a negative 2. So we have a horizontal asymptote right here at y equals 2, or at f of x equals 2. That's our horizontal asymptote. We also have a vertical asymptote right here. This has some infinite discontinuity going on. Okay? What's the one point that is not allowed to be plotted right there? -1, where x is equal to a -1. This is your vertical asymptote. So you're going to label your vertical asymptote at x equals -1. So right here, if I go back to my problem, I do have a horizontal asymptote and I have a vertical asymptote. So I'm going to write the word vertical. The vertical is at x equals a -1, and I do have a horizontal where f of x is equal to 2, or where y is equal to a 2. All right. What's my domain? What points are actually being plotted? Are all of them being plotted? Yeah, we have to do a union. Okay? We have to do a. So if I go back here, see right here, there's infinite discontinuity. So what's the only point that I can't plot for my domain? Just a -1, right? So how do we write that? So we go from what? We go from negative infinity to what number? To a -1. We remember soft bracket, and you put union with -1 to infinity. Now, how would you write this in set builder notation? Here's how you write it. The set of all x values such that x simply cannot equal a -1. However, x is still, you're plotting basically all real numbers except for -1. This would be your answer in set builder notation. This is in interval notation. Right now, I just want you to use interval notation, but I want you to see the difference between the two. All right, so far we've covered 2 scenarios. We're down to the final scenario. CJ, I think you asked me earlier. You said, what if m was what? Right, so if. So same function, okay? I'm not going to rewrite that. If m is greater than n. All right, so if the exponent in the numerator is bigger than the exponent in the denominator, then what? Then there is no horizontal line. Okay? So then there's none. Okay?
So the asymptotes for the vertical.
So the vertical, the vertical is whenever the denominator equals 0. We're going to cover the vertical. All right? But we have 3 different scenarios. Either it's m is less than n, m is equal to n, or m is greater than n. Now, underneath this one, put a little star. If n is 1 degree higher than n. If it's 1 degree higher than n. So what if, let me give you a what if, ready? If f of x was 4x squared plus 1 over x minus 2. Can everybody see right here that m is 2 and n, even though you can't see it, n is 1. So if m is 1 degree higher than n, then there is a slant, also known as an oblique asymptote. So there's no horizontal asymptote, but there is a slant asymptote. All right, what we're going to do is we're going to find the slant asymptote for this example problem. All right, we're going to find the slant asymptote for this example problem. Then here we're going to talk about vertical asymptotes for the third problem. Okay, for the third problem we have some vertical asymptotes. So right now, what I'd like you to do, I want you guys to do x minus 2 into 4x squared plus 1. Now, sometimes you have to do long division. Sometimes you can do synthetic division. Do we have to use long division here, or can we use synthetic division? We can use synthetic because the degree right here is simply a 1, and there's the number 1x minus 2. So let's just use some synthetic division, and I'll explain to you how to find your slant asymptote. What number are we going to use right here?
2.
Just the number 2. How many x squareds do we have?
4.
X to the firsts.
Oh, 0, good.
0x to the first, and we have 1x to the 0. So we're going to use synthetic division right now. Bring down the 4, multiply, add, multiply. I want you to understand the remainder right here, we really don't even need to worry about it. Here's what we need to worry about. This represents the x to the firsts. This represents x to the 0. So x minus 2 went into 4x squared, 4x plus 8 times, with the remainder of 17 over x minus 2. Your slant asymptote, everybody, for this problem is this. F of x equals 4x plus 8. That would be your slant asymptote. So whatever you get right here, that's your slant asymptote after you use synthetic division. But you only have to do this in one situation, when this is simply 1 degree higher. Okay, that's the only situation. If it was 2 degrees higher, if that was a 3 and a 1, you wouldn't have to do it. It's only when it's 1 degree higher. So what I would like you to do, take this right here. It's in your journal. Take that and put it in your graphing calculator. I want you to be able to see it. So right now, take this right here, put it in your graphing calculator. Clear this out. Clear this out. Bless you. 4x squared plus 1, x minus 2. When you hit graph, this graph looks a little bit different than some of your other rational functions. You're going to hit y equals and go down here and type in 4x plus an 8 and hit graph. This right here will continue to get closer and closer and closer to 4x plus 8. It'll get closer to this slanted asymptote. I'm going to change the window. I'm going to go down to where the y minimum is at negative 100. And I'm going to change the y scale to 10. So you guys can see how it gets closer and closer and closer. There's your function. There's your slant asymptote. Just gets closer to that slanted asymptote. Okay? Now, we go to our problem right here. This one does not have a slant asymptote, okay? This is x to the first. Down here we have x squared. So without even graphing it in the graphing calculator, for problem number 3, what type of horizontal asymptote do we have? I think I heard somebody say. This degree is smaller than this degree. What situation is when we have m is less than n? Yeah, so m is less than n, so this is going to be f of x equals 0. That's our horizontal. We actually have 2 vertical asymptotes. How do you locate your vertical asymptotes? Whatever number plugged in here and whatever number plugged in here makes that denominator equal to 0. Those are your answers. What number would be a bad number to plug in right there and right there? -1 and a +2. So you have vertical asymptotes at x equals -1 and at x equals +2. Anytime the denominator is equal to a 0, all right, and the numerator and the denominator don't cancel each other out. That's where the holes are in the graph. We'll talk about that later. Right now, if you can make this equal to 0 and nothing cancels out, then you have some vertical asymptotes. Go to the graphic calculator, get y equals. This is our last one here that we're doing on the video. And the numerator we had, what, x plus 3? And the denominator we had x, so plus 1, and x minus 2. Okay, zoom and 6. Zoom 6. So right here, that right there is our horizontal asymptote, and we have 2 vertical asymptotes. We have a vertical asymptote right here, and we have a vertical asymptote right there. Now, our domain, it's broken into how many? 3 different categories, right? We got a domain over here, we got a domain here, and we have a domain here. So what's this domain? Just by itself, what's this domain? -infinity to -1. What's this domain right in here? From what to what? Over here. -1 to 2. Good. Now this one over here. +2. So what I want you guys to do when you guys are looking at a graph, break into different sections. This is your first section that's being graphed. This is your second section that's graphed. This is your third section. Okay? So now we're going to go back and we're going to write it all together. So the domain goes from -infinity to -1, union with -1 to +2, union with 2 to +infinity. And that right there is your domain. Okay? If you were to write it in set builder notation, you'd say the set of all x values such that x cannot equal a -1 and x cannot equal a +2. X is an element of all real numbers. What I'd like you to do next is I'd like you to simply do all of number 4 on your own. Just graph it, talk about the domain, talk about the intercepts, talk about the asymptotes, all those things. All right?